Hello students, welcome to Yupp Master. So in our last class we discussed inertial and non-inertial frame. So till now in Newton's law we reached to that particular point, and let's first see what we have done till now. Let's revise few points, and then today we are going to solve problem on inertial and non-inertial frame. Now see, so what we discuss, that inertial frames are those frames on which Newton's laws are valid. That means any observer on inertial frame if he observes that there is no force on the body, so net force on the body is 0, and he observes that acceleration is 0, then frame is said to be inertial, right? So this is the way we check whether our frame is inertial or non-inertial. Okay, so if this condition is met, frame is said to be inertial, right? If this condition won't met, then frame is non-inertial, right? So this is the way we check inertial frame. Once we check the inertial frame, any frame which is accelerating with respect to inertial frame, so this is inertial, and with respect to this frame, what I observe, that this another frame is having some acceleration. So as with respect to inertial frame, this frame is having acceleration, this is called non-inertial frame, and you cannot directly apply Newton's law the way you applied for inertial frame. So you need to do some adjustment to apply Newton's law from non-inertial frame. So any frame which is having acceleration with respect to inertial frame is non-inertial frame, right? So if I call this frame as S, this frame as S dash, then this frame will have acceleration with respect to inertial frame, then it will come, or it will become non-inertial frame. Now second point, we have already discussed that when you go from one non-inertial frame to another non-inertial frame, the value of acceleration and the value of the fictitious force we need to apply on the body changes, right? So for different frame, the value of fictitious force and the value of relative acceleration what we are going to get will be different. So I already discussed this point in the last class, and this is the last point, that to apply Newton's law from non-inertial frame, you have to add one fictitious force which is called pseudo force. So what we did, we took one body and we observe this body with respect to inertial frame. So with respect to this inertial frame, we observed this body. So we observed that net force F is acting, and due to this force this body is accelerating, right? And if I want to change frame, if I want to go to frame which is accelerating with respect to this frame, say with acceleration of S dash with respect to S, where this is S, inertial frame is S and non-inertial frame is S dash. Then if I want to apply Newton's law with respect to this frame, in the last class we have seen that I need to add one term which I call pseudo, whose direction, or I need to add one force which I call pseudo, whose direction is opposite to the direction of acceleration. So mass into acceleration of S dash with respect to S, direction opposite, right? So this we call pseudo. So those who have seen our last class, they know this point, and those who haven't seen the last class, they can go through the last class where I derived the expression, right. So today we are not getting into the derivation part, I am just telling what we discussed till now. So if this is the situation, then in last class we got a real force acting on the body plus pseudo force will give you mass into acceleration relative. Okay. So if you add real force with pseudo force, then you are going to get acceleration with respect to non-inertial frame. So this is a relative acceleration. When you go from one non-inertial frame to another non-inertial frame, the value of this term will be different. Accordingly, the value of this term will be different, but this quantity will remain same from all the frame, whether they are inertial or non-inertial. So real forces will be observed same. So this real force, whether you are observing from inertial frame or you are observing from non-inertial frame, is not going to change. And to get the acceleration, when we switch frame, when we go from inertial to non-inertial frame, I need to just add one term which I am calling pseudo, right. So pseudo force formula was negative mass of the object, acceleration of the non-inertial frame with respect to inertial frame, right. So this we discussed in last class. After that we discussed few problems where I made you understood that real force will come same from all the frame. Okay. Now this we have already discussed in the last class. Let's move to next problem. Look at this one. So similar problem I already discussed in the last class. Here I am asking what is the reading of this spring balance. So spring balance is attached to spring block pulley block system, and it is kept inside a lift which is going up with acceleration g by 10. What would be the reading measured by the spring balance? That is the question. So pulley, string, spring balance, all are light. So to find the reading of this spring balance, I require tension here, right. If I assume tension in the string is T, because pulley is massless, tension here will be 2T. So if I can find the value of 2T, 2T divided by G will give me the reading, right. Force divided by G will give you the reading measured by the spring balance. We already discussed this point. Now I can observe motion of these two blocks with respect to observer standing on the ground, or I can observe motion standing here. So with respect to person standing on the ground or with respect to person inside the lift, I can observe the motion. I am going to get the same value of the real force. Okay. Now as we have already discussed non-inertial frame, I solve this problem with respect to person inside the lift. As lift is accelerating up, this observer will accelerate up. Okay. So this observer will be non-inertial frame. So with respect to this observer, all the real forces will appear same. See, if I assume, just to make calculation simple, G is equal to 10 meter per second square. Okay. I am assuming G to be 10 meter per second square, just to make things simple. So this lift is going up with acceleration. If G is 10, this is 1 meter per second square. So this is the acceleration of the frame. Let's call it A0, right. So this observer observes that tension on this block upward, mg 15 Newton, and then ma direction opposite. A is 1, mass is 1.5, lift is going up person is going up with acceleration 1, so he will add pseudo force in downward direction. Pseudo force, mass into acceleration 1.5 Newton. Now let's draw free body diagram of 3 kg block. Tension T up, its weight mg 30 Newton down, plus pseudo force as frame is non-inertial. So pseudo force, mass of the block, acceleration of the frame, direction opposite. So this we are getting 3 Newton. So person is standing inside the lift, say he observes that block goes up with relative acceleration A relative and this block comes down with acceleration A relative. So what I'll write, T minus 15 plus 1.5. Okay, so T minus this real force mg, pseudo force 16.5 in downward direction, 16.5 is equal to mass into acceleration 1.5 into A relative. Then this, look at this block, it is accelerating down with respect to this observer. So 30 plus this 3, 33. 33 minus T is equal to mass is 3 into acceleration A relative. Okay, I want T, okay, tension. So I can multiply first equation to 2, this equation to 2, and subtract these two. So minus plus minus, right? If I subtract these two are getting cancelled out, and this side we have, I can see 3T, and then look at this one, this is 33, this is 33, minus 66 is equal to 0, that means T is equal to 22 Newton, and I require 2T, 2T will be 44 Newton. As a spring balance measures mass, I will divide this value by G. So reading will be 2T divided by G, that means 44 divided by, that means 4.4 kg will be the reading. If I am taking G as 10, you take 9.8, right? So I hope approach is clear. I am going to get the same result even if I observe from the ground, but it's easy to observe the motion with respect to lift frame. From lift frame you will observe that whatever acceleration this block is having in upward direction, other block will be having same acceleration in downward direction. So 3 equation what I supposed to make from the ground frame got converted into only 2 equation. You can see first equation and second equation. From ground frame if you want to solve, you will assume that acceleration of this block is A1, acceleration of this block is A2, okay, tension in the string is another unknown, so total number of unknown will be T, A1, A2, so 3 forces. So we require 3 equation, Newton's second law for this one, Newton's second law for this one, and then constraint equation. So 3 equation, after solving you are going to get answer. Here we are getting benefit of constraint equation. We are not writing constraint here because with respect to lift frame, whatever be the acceleration of this one in upward direction, same will be acceleration of this one in downward direction. So only this is the basic difference. Otherwise from any frame you can solve the problem, you are going to get same result, right? So I hope now approach is clear. When we want to solve problem from non-inertial frame, we need to just add pseudo force. Now let's see another example. Look at this one. First go through question. in the given figure, what should be the minimum horizontal force applied on the cart in order that the block remain stationary. Look at this line, block remain stationary relative to the cart. So with respect to cart, blocks are not moving, right? As you can see, unbalanced force on the cart will accelerate. So if I assume that acceleration of cart is a naught, for there to be no relative motion, the acceleration of this one has to be a naught and the acceleration of this one has to be a naught. So if all are having same acceleration, then obviously there won't be any relative motion. So this is what observed by a person standing on the ground. So person standing on the ground, he observes that all three components of the system have the same acceleration and they are moving forward. As they all have the same acceleration, I can consider this whole thing as one system. So condition for something to be considered as system, you can see this whole thing is having same acceleration, okay. And if I have considered this as system, I'll just draw all external forces on the system, okay. So external forces, I can see mg here, the reaction coming from this one, reaction coming on this one, then mg of this one, this is m2g, and this one m1g, okay. So these are the forces acting on the system, external forces on the system. There will be other forces like normal reaction here and here, normal reaction here and here. On this system they will become internal, they will cancel each other. So this block will exert normal on this one and this block will exert normal on this one, they will cancel each other. For this as a one system. So similarly normal coming here and normal coming here, they will cancel each other. Similarly if I take the tension, so tension on pulley in this direction, tension on the block in this direction, they will cancel. Here it will be in this direction, here it will be in this direction, they will also cancel each other. So these all are internal. If we talk about the acceleration, we have to consider only external because internal will get cancelled out. And you can see on system there is F acting in horizontal direction and the remaining forces are vertical. So that means this F will accelerate the system. If this F is accelerating the system, I can write F is equal to M plus M1 plus M2 G, sorry, A naught right. So person is standing on the ground, observes that all the three moving in forward direction with acceleration A naught. For that I wrote the equation. Now as in question it is given, you need to find out the value of F for which there is no acceleration or there is no relative acceleration between this cart and the block. So if I observe motion of M1 and M2 with respect to block, just to get other equations, what I am going to observe. So I'll put observer on the cart, as observer is on the cart which is accelerating with A naught. observer is on the cart which is accelerating with a naught with respect to this frame. I'll remove all other forces which are not needed. Now, if I draw free body diagram of M1 along the motion t in this direction, with respect to this observer there is no motion, right? T in this direction, for this one t in this direction, m2g in this direction. Now, as our frame is non-inertial, he will add pseudo force. Mass of the block, acceleration of the frame, direction opposite. M1 a naught, and similarly here M2 a naught. And then other forces will also be there, like normal action on this block, let's call it N1, and then M1g. As we are just observing this block, normal and M1g will be external to this block. Similarly, M2 is in contact with the cart, one normal will come like this, N2. So this observer, as he is not observing any motion for M1 and M2, he will apply Newton's first law in y direction, Newton's first law in x direction for M1. Similarly, this observer will apply Newton's first law in this direction, as he is not observing any motion here and he is not observing any motion here. See, if this block is not moving with respect to this observer, with respect to this observer, the length of this string is constant. If length of this string is constant, length of this string is constant, that means this is not going in y direction. So the whole system will go like this. So here, instead of writing all the equation, I'll write only those equations which are necessary. So for this block in this direction, he will write T minus M1 a naught is equal to 0, Newton's first law, in this direction. I am not writing equation in y direction because there is no use. Similarly, same observer will write Newton's first law in this direction. This is the direction along x-axis. So N2 or in this case this is not necessary, so I'll remove this equation. I'll just focus on y direction. In y direction, see, if there is no motion, that means T minus M2g is equal to 0. So for M1 block, for M2 block, we got this equation, and if I simplify, I am getting M1 a naught will be equal to M2g. That means we are getting a naught is equal to M2g divided by M1. So here if I write the value of a naught from here, then I'll get the value of F needed to know relative motion between M1 and cart and M2 and cart. So we are getting M plus M1 plus M2 into M2g divided by M1. So this is the force. If this is the critical value of the force for which there is no relative motion. If you apply a small force, smaller than this what you got, then what happens? The system will move like this. This block will be moving relative to this cart in downward direction, and this will be moving in forward direction. If force is greater than this value, if force you are applying larger force than this force, then what happens? Cart will move this way, this will go up, this will move in backward direction. So this is the critical value for which there is no relative motion between this, and there is no relative motion between this and this. So I hope this is clear. So some part of the motion I observed from the ground frame. So this I wrote from ground frame standing here, and the remaining part means these two equations I wrote from this observer. So depending on whose motion is simple to observe from the ground and whose motion is simple to observe from non-inertial frame, I will switch the frame for the same problem. Previous case, for same problem I was in non-inertial frame. If you look at the previous one, I just went inside the frame and I observed the motion of both the blocks. But here what I am doing is, some part of the motion I am observing from the ground, as the motion of capital M can be easily observed with respect to ground. So for this one I am writing from ground, and these two I find easy to observe from this frame, that is why I am writing from that frame. I already told you you need not to change frame, you can solve whole problem from the ground frame only. Look at this one. If instead of this observer, if I want to observe the motion of this and this block with respect to ground observer, so this observer, what he will observe, that block is going with A naught, what he will write then? So he observes, the person standing on the ground observes that this block is going with acceleration A naught. So this is the only unbalanced force which will provide this acceleration. So first equation he will write T is equal to m1 A naught. So instead of Newton's first law, now person standing on the ground is applying Newton's second law on the block, because he observes the motion. Similarly, this observer observes that block will remain at the same height and keep moving in this direction. That means in y direction there is no motion. If no motion in y direction, so y direction he will write Newton's first law, m2g is equal to 0. And look at these two equations what I wrote for this observer, and look at these two equations what I wrote for this observer. They are ultimately the same equation, only thing format is different. Here in both the direction Newton's first law, here for this one Newton's second law, and for this one in y direction Newton's first law. So again I am telling, you can solve any problem standing on the ground, but sometimes it becomes simple if we change the frame, like in next problem. Okay, so this is clear. Now I start increasing the level of the problem, right? Now see next one. Again I am telling, you can observe both the motion standing on the ground. So if this is the system, here this string is attached, right, and actually this string passes through the pulley, then again passes through pulley and connected to this block. Okay, so there is a small problem in diagram, there is no attachment here. Okay, so don't consider this attachment, that is not there, right? So I hope now it is clear. This string passes through this pulley, then again passes through this pulley and connected to block M. Now if I ask what would be the motion of small m, so obviously because of this tension in the string, this arrangement will move in this direction. So after some time this wedge will be somewhere here. Okay, so wedge is somewhere here, the block, this block this block will come down further, block will be here. So this is the new location of wedge, and this is new location of block. As you can see, the motion of the block is something like this, while the motion of wedge is something like this. So wedge will move in horizontal direction, but the block will move in horizontal direction as well as vertical direction. So the resultant motion will be something like this. As the motion of block from ground frame looks complicated, instead of observing block from ground frame, if I observe block, with respect to this frame, so standing here, if I observe block, what I will observe, that block is just going down. So block I will observe from pulley frame, and wedge I will observe from ground frame, like what we did in the previous case, same thing, right? So if you draw free body diagram of wedge, so I want to observe wedge from the ground frame, which is inertial frame. Directly I can write F is equal to ma. If I draw free body diagram of wedge, so whenever pulleys are connected, I already told you, consider pulley as part of the block. So these two pulley I have taken part of the wedge. Okay. Now this side string will exert force T, so I will add one force T here. This side of string T, T, this side in downward direction T, this side in downward direction T. Okay, this is the force exerted by string on wedge plus pulley system. Then I can see reaction coming from here, R. I will draw R here. Then I can see capital Mg field force drawn. As the block is in contact with capital M, so capital M will push the block this way, and this block will push the wedge in opposite direction. So normally action will come in this direction. Now if I assume that wedge is having acceleration a naught, assume that this wedge got acceleration a naught. So along the direction of acceleration, t in this direction and in opposite direction, so t minus n is equal to mass into acceleration. T minus n is equal to m a naught. This is for wedge, right? Wedge over. Now comes block. So I will remove this free body diagram. So for wedge, we already wrote equation. Standing on ground, we wrote this one. I will remove this wedge. Now let's observe block. For block, see, with whatever rate this is getting reduced, because this is constant, same rate this will get increase. Or you can write constraint with respect to this one. If I want to write constraint, x capital M, and this length is constant b, and with respect to this one pulley, let the position of this small m is y, small m with respect to capital M, pulley is the part of this capital M. So if I write the length of the string, then I'll get x capital M plus b plus y small m with respect to capital M is equal to L. Let's differentiate this one. So if I differentiate this equation twice, then I'll get the relation between the acceleration of capital M with respect to ground and acceleration of small m with respect to capital M. So if I differentiate here, so I'll get a naught, and here I'll get, after differentiation, this is reducing, so minus sign, and then this is plus acceleration of small m with respect to capital M is equal to 0. That means relative acceleration we are going to get same. So we have already discussed how to relate acceleration using constraint. So those who haven't attended those classes, just go through those classes. I discuss each and everything in detail, how to establish the relation between acceleration, right? So acceleration of this block with respect to pulley will be in downward direction a naught, right? From here we can conclude that. Now I'll remove this constraint equation. So person is standing on the pulley, what he is going to observe, that block goes down, this observer observes that block goes down with acceleration a naught, and forces what he is observing, tension T upward, mg downward, right, normal in this direction, and as his frame is non-inertial, he is on the wedge which is accelerating with a naught, he will add pseudo force in this direction on the block, that is ma naught. So one motion in y direction, another motion in x direction. So this observer observes that block goes down with acceleration a naught. For y direction he will write mg minus t is equal to mass into acceleration, mg minus t is equal to mass into acceleration, and for x direction he is going to write n is equal to ma naught. Newton's first law in this direction and Newton's second law in this direction. So these are the three equations we made, and this was for wedge mass was capital M. So I will write capital M over here. This is capital M. If I add these three equations, t getting cancelled out and n getting cancelled out, we are getting mg is equal to capital M plus 2 times small m a naught. That means a naught is small mg divided by capital M plus 2m. So this is the acceleration you are getting, acceleration of the block in y direction you are getting with respect to wedge. So if I apply relative acceleration formula, acceleration of block with respect to wedge, acceleration of block with respect to wedge is acceleration of block with respect to ground minus acceleration of wedge with respect to ground. This I want to find out. Question is, find the acceleration of body m relative to the horizontal surface, means with respect to ground. So acceleration of block with respect to ground can be written acceleration of block with respect to wedge plus acceleration of wedge with respect to ground. These two I need to add. Acceleration of block with respect to wedge, that is coming with respect to wedge, it is having acceleration a naught. A naught j cap with minus sign, then acceleration of wedge with respect to ground, wedge is going with acceleration a naught I cap. So resultant of these two, or I can say mod block with respect to ground is root 2 a naught, and value of a naught we already have. This I will substitute here. This is the result we are getting. Okay. So instead of observing block standing on the ground, I observed block standing here and I observed wedge standing on the ground. So from ground frame I can see the wedge goes in x direction. I know the motion of wedge from the ground frame. That's why it was convenient to observe the motion of wedge with respect to ground. Now block, instead of observing motion with respect to ground, I am observing with respect to this wedge, because I can see that with respect to this wedge it will come down. So as I was able to easily analyze motion of block with respect to wedge, I am observing block with respect to wedge after adding pseudo force, because frame is non-inertial. So this problem, previous problem, these were simple problem. You can easily solve these problem from ground frame only. But look at the next problem, then you will understand. See this one. Mass of wedge and the block both are m. This one is m and this one is m. Let this be A and this be B. Okay. As there is force tension on the wedge in this direction, wedge will move forward. So after some time the wedge will come, wedge will move forward. Okay. See, wedge has moved this much distance. So as this part of the string got released, this side the block will come somewhere here, the block will be somewhere here and the string will be like this. So wedge goes in x direction, block with respect to wedge will come along the incline. As wedge is also moving, motion of the block will be something like this. So motion of wedge is simple in this direction. Motion of wedge with respect to ground is now complicated. Even in previous case it was little simple, but here motion of this block is more complicated. So for these type of situation, it will be better you observe the motion of wedge from the ground frame and then you observe the motion of block from wedge frame. I hope now this point is clear. Okay. So motion was relatively complicated with respect to ground. So I'll assume wedge is having some acceleration a naught. From ground observer, this wedge will definitely go this side. Let that is a naught. With respect to this observer, this block will definitely go along the plane downward. So I'll assume this acceleration to be a relative, because this is relative to this observer. Up to this point, no doubt, very simple situation, right? First thing, relating this with this one using constraint. So if I take reference here, this is position of A and this is position of block B with respect to A. So with this one, I can write equation of constraint xa plus xba is equal to L. If this distance decreases with time, then in terms of velocity this is minus Va, and then this is Vb with respect to A, differentiation of constant is 0. If I again differentiate, acceleration of B with respect to A. So acceleration of B with respect to A will have same magnitude as that of A. Acceleration of A is A naught. That means this relative acceleration will have magnitude A naught. This is from constraint. Again I am telling, I have already discussed constraint. If you have missed that class, go through that class again, okay. Then come to this one. So constraint, first relation I have, once I establish relation between acceleration, now it's time to write Newton's law. Okay, for that I require free body diagram. So from free body diagram, if I draw free body diagram of wedge and pulley, I can see one tension here, one tension here. So T, and then this will exert normal on the block wedge this way. So on wedge, normal will be like this. From surface, reaction will come R, and then one field force mg. Now this is complete free body diagram. Small m, this is a complete free body diagram, and due to all the forces in horizontal direction, it is having acceleration A naught, which is observed by observer standing on the ground, which is inertial frame. So what I'll write, if this angle is say theta, this angle is theta, this angle will be theta with normal, with vertical, this will make theta. So I'll resolve all the forces along the motion and perpendicular motion. So along x direction, along y direction I need to resolve. So this tension will have two components, one in this direction t cos theta, another in this direction t sin theta. Similarly this normal will have two components, one in this direction n cos theta, another in this direction n sin theta, along the angle cos perpendicular to that sin. Now as I have resolved the component of this tension, I will remove this tension, resolve the component normal, I will remove normal. This is what I am going to see. Now all the forces are along and perpendicular, right? So look at the free body diagram in x direction t and n sin theta. So first equation I am going to write t plus n sin theta, opposite direction t cos theta minus t cos theta is equal to mass into acceleration. Simple equation, right? So motion along x direction, I have written the equation. Now wedge over, if you feel like writing for y direction, write one equation for y direction, but as it is not needed, I am not writing that equation in y direction. I am just writing equation in x direction. Okay. Let's draw free body diagram of block. So free body diagram of block, normal action mg along the plane tension, these are the real forces, okay. And as our frame is accelerating, I need to add pseudo force, right. So pseudo force, mass of the object, acceleration of the frame, direction opposite. So pseudo force will be like this, ma0. This is the complete free body diagram, all real forces and the pseudo force. And the person is standing here, what he is observing, that block goes along the plane with acceleration a0, right. So what I will do, I will resolve all the forces along the plane and perpendicular to the plane. So tension is already along the plane, normal is already perpendicular to the plane, so these two are along the plane and perpendicular to the plane. Now mg and a0 I can see they are not along the plane and perpendicular to the plane. So this angle is theta and here this angle is theta. I will resolve mg first along the plane and perpendicular to the plane. So mg cos theta, mg sin theta, mg I already resolved. Similarly ma0 cos theta, ma0 sin theta, okay. So ma0 cos theta, ma0 sin theta. So ma0 and mg we have already resolved. I'll remove this ma0, I'll remove mg. So this is, we have along the plane and perpendicular to the plane. Along the plane he observes that block is having relative acceleration a0. So this observer, what he is going to write, let's see that. So net force along the plane ma0 cos theta plus mg sin theta minus tension T up is equal to mass into acceleration. Written by this observer, okay. Let's call it observer A, observer B. So this is for observer A, now for observer B. Block also I am calling AB. Let's give different name. Instead of AB, let's call them S dash. So for frame S, I have already written equation, S over S dash I am writing. So S over, now S dash. So same observer observes that block is not losing contact with the wedge. So in this direction forces must get balanced. So perpendicular to the incline forces must be balanced. That means what I can write, mg cos theta must get balanced by mg cos theta minus ma0 sin theta minus n is equal to 0. For frame S, motion of the wedge, from frame S dash, motion of the block. In this direction there is motion, in this direction there is no motion. So after adding pseudo force, we will resolve the component along the plane and perpendicular to the plane. So perpendicular to the plane, no motion is being observed. So Newton's first law, and along the plane there is motion. That's why Newton's second law. If you count number of unknown we don't know value of tension, we don't know value of normal, and we don't know value of A naught. So T unknown, N unknown, and A naught unknown. So there will be 3 unknown, T, N, and A naught. So these are the 3 unknown we have, and the number of equation we have made 3. So solving these 3 equation, you can find out the value of acceleration of block and acceleration of wedge. Do remember that this A naught is the acceleration with respect to wedge. So acceleration of B with respect to ground is nothing but acceleration of B with respect to A plus acceleration of A with respect to ground. So B with respect to A is this A naught. In that you need to add acceleration of A with respect to ground, then you will get B with respect to ground. So generally what happens, in hurry student commit mistake, they mark this as acceleration, but generally this acceleration will be asked, acceleration of the block will be asked with respect to ground. So this acceleration is with respect to wedge. With respect to ground, you need to add acceleration of wedge with respect to ground. So I hope this point is clear. So if you are asked to find out tension, acceleration, now you can answer, right? So today we discuss how to use pseudo force, right? And when to use, when not to use. Slowly with the practice you will come to know. So solve more and more problem, then you will realize when to be on the ground and when to change the frame. Okay, so simple logic is like, if you can easily observe the motion with respect to some non-inertial frame, then only you switch the frame. Otherwise all the problem can be solved from the ground frame, right? So this concept we kept dealing in subsequent topics also. So our next topic is Newton's law we covered, inertial non-inertial frame we covered. Our next topic is friction. So friction also we will see the application of this one, right? So I hope everything is clear till now, and you must have enjoyed today's class. So thanks very much for watching.